Hello everyone. So with this example, we'll practice a little bit looking at axial stress. Axial stress is where you have a force that's pulling in the length direction of your member, longitudinal to the member under consideration. In this case, we have an example of tensile axial stress because the applied force is elongating the member, or attempting to. If these forces were in the opposite direction, we'd have compressive axial forces. A reminder, stress is always force divided by area, okay? Stress is always force divided by area. The critical thing is to make sure you always identify the correct force and the correct area that force is applied on. That's the trick to making sure you get stress values that are correct. So in our case, we're going to play with longitudinal stress or axial stress. Let's practice it. We're going to use an example we have here. We have some kind of a cylinder. We can pretend it's a concrete cylinder or a steel cylinder. I've made up all the properties, the applied forces, and so on. This cylinder measures in length 1,234 millimeters. We have a tensile force of 1,235 kilonewtons applied to it. We're using metric units. And we assume that the diameter of that face is 125 millimeters. So let's figure out what the stress is that's been applied to this cylinder. Great. We make sure we are looking at the correct force. That's the force, the only one given. We have a force. For the area, the force has been applied on this area, right, that circle, and it's the same for the bottom. So we can find the area given the diameter of that shape. Okay, so the force we already have right here, but we have to figure out the area. So we remember that the area for a circle is pi times the radius squared. So pi times, we have the diameter. The diameter is 2 times the radius, so half of that is the radius. 125 millimeters divided by 2 squared. Make sense? And then when we work that out, we get 12,271.846 millimeters squared. Okay? So look at that. We have a force. Now we have an area. So simply, let's put it into our equation, our formula. Let's put it right here. Stress then is equal to, our force is 1,235 kilonewtons. Our area is 12,271.846 millimeters. So now we just divide the two numbers, right? Not quite yet. We have to make sure we're using the correct balance of units. I mean, if you calculated this out, you'd get an answer that's in kilonewtons per millimeter squared. And that'd be correct if you're given no parameters as to what units to use for stress. But if you remember from our lecture, the typical metric units that we use for stress are either kPa or MPa, where kPa is kilonewtons per meter squared, and MPa, a good conversion, is newtons per millimeter squared. Here, well, we kind of have kilonewtons at the numerator and millimeters at the denominator. So if we want our answer in kPa or MPa, we have to do something here. So I choose to simply convert this from kilonewtons to newtons and leave the area in millimeters squared, so I'll get an answer in MPa. Now when it comes to, say, your tests or exams, you will typically be given what units to display this in, or you'll get answers that already have units in them, and only one set of numbers and units will work out correctly. Okay, so in our case, I'm going to convert this to newtons. To go from kilonewtons to newtons, I multiply by 1,000. 235,000 newtons. I leave the denominator untouched. 12,271.846 millimeters squared. And then when I divide these two numbers, I get 100.637 Newton per millimeter squared, or MPa. Okay, it's that simple. So the critical thing again is find the force, find the area, make sure they're the right force in the right area, and then before you divide them, make sure you work out the proper units to make this work out, to either get it in kPa or MPa. Okay, that's simple. So what we're going to do now is kind of repeat this process, but I'm going to change these dimensions so that we get imperial units, right? Pounds, inches, that sort of stuff. So give me a second, I'm going to clean this up, and we'll be ready to go. Okay, so for our imperial example, imperial units, I'm going to pick a force. I completely make up the number of 6,052 pounds. Okay? And then I'm going to completely make up a diameter of 6 inches. Okay, completely made up. And then this length here, it doesn't come into play if you've seen the first part of this video, but I'm going to call this 1,234 feet. Okay? It doesn't matter for the purposes of this example. So again, what we have to do is divide the force by the appropriate area. The force is given here. The area we have to calculate from the given diameter. So for the area of a circle, we remember that it's pi r squared. Pi times the diameter is twice the area, so it's twice the radius. So the radius is half that, 6 inches divided by 2. All of this squared, and we get 28.274 inches squared, because units matter. Okay, we have the force, we now have the area. Let's put it in our formula, because this we now have, this we now have. Let's make some magic happen. The force is 6,052 pounds. The area is 28.274 inches squared. And now we just divide the two numbers, right? Well, not quite yet. We have to make sure the units work out. So the units that I gave to you during the lecture, typically either PSI or KSI. I think I gave you one more too. So either pounds per inch square for PSI or kips per inch square for KSI. Well, we have pounds inch square, so we can get something in PSI. It works with this. So yes, we can simply divide the two numbers. When we do 6,052 divided by 28.274, I get 214.046 PSI. This is important because units matter. In structural engineering, engineering in general, numbers without units are allowed to be without units if they don't have units, like strain. And even then, we usually convert it to percentage. 214.046 PSI. Not bad, right? Relatively simple. Stress is force divided by area. Great. Now look for the description of this video at the bottom. There'll be links to other examples. If it's not there, There'll be other examples linked in the original lecture. That for sure will be linked for you in the description. Thank you for your time and have a lovely day.